So the next talk will be by Richard from NSF NORLab on variable stars in M31 stellar clusters. Do they need sound Okay, and then I'll give you the 3 minutes to get it right. Sorry.
Yeah, thank you very much. Sorry, hope you can hear me, everybody. Yeah, thank you. I'm Richard Smith, a postdoc researcher at NOIR Labs Gemini North Observatory. I'm just going to talk through a recent work looking at variable stars in M31 clusters, with an emphasis on really how it highlights, because it is focused on Hubble data, but an emphasis on the highlights on how it can be relevant to the upcoming missions and surveys with Roman. So why are we actually interested in stars in stellar clusters, and in particular variable stars? So stars within clusters are really useful because with the because the largely homogeneous in age and metallicity of cluster stars, and we can constrain their physical parameters through the, for example, mass, age in evolutionary phase. Variable stars in clusters are particularly useful because through using these cluster properties, we can then inform, for example, not just the big, bright, and yes, interesting variables, but the variables with much smaller amplitudes can be valuable and interesting for example, informing us on stellar pulsation models and stellar interiors. So that's why, just as a whole, variable stars within clusters are really particularly valuable. And just to highlight here on the right-hand side is a map of the M31 star clusters from the FAT survey. So the FAT survey is the Panchromatic Hubble Andromeda Treasury. This is the data set that we have used for this study. And so the FAT survey, just very briefly, mapped about a third of M31's disk. It used UV to near IR filters in 2 instruments. We focused on ACS, primarily for the increased optical depth of its 2 most populous filters. And just on the left, on the right here, is a map of the FAT survey itself in terms of the number of visits to each region of M31. But the key takeaway for this study, and the immediate relevance for Roman, is that FAT was not designed for time domain studies. The reason we are able to perform this study is because of this design on the right of the survey. So you can see it's roughly divided into 23 bricks, rather conveniently shaped like bricks. And in essence, the survey visited each half of these bricks, roughly 6 months separated in time. And the overlaps, which are shown by the number of visits, allows us to study variable stars across M31. And so, for example, with Roman, this emphasizes that even if we don't do a targeted survey, we can still get valuable information if there are any overlaps across whichever patch of sky, in this case, M31. But for this work, so the table on the left just runs through basically the constraints that we applied to the FAT survey to narrow down the number of stars that are known in the FAT survey to those within clusters. So rather than remeasuring all the photometry of all these stars, there's a paper by Williams et al. 2014, which has over 117 million stars from the FAT survey. And that is our photometry catalog that we have used. And so, as I say, we narrowed it down from this 117 million to the stars within clusters, particularly luminous stars. So basically, because of the crowded cluster environments, we wanted to have a good threshold above which we knew that we'd have a good chance of picking up these stars. And then on the right-hand side is the first stage of how we identified these variables. So there's 3 stages. This is very, very abbreviated, but effectively we looked at the fat photometry first and looked at the light curves to see, did any of these cluster stars, luminous cluster stars, change? And yes, we consider this a light curve. It's not the best, but we can at least say, has something changed or not? Based on the median value of, sorry, the mean value of the light curve. And this gave us a list of candidate variable stars within these clusters. We then go on to perform difference imaging using the optimal image subtraction software. And this on the right just shows 2 example difference images for 2 different stars. And we do this to verify any detection of variability from the light curves in these different images. So we perform source detection, and any star with a source, a counterpart source within 1 ACS full width half maximum is classed as a confirmed variable in this case. And again, just re-emphasizing, we don't do any photometric measurements. Again, why reinvent the wheel when the FAT catalog is a very well understood and very good wheel. And then the third step is to perform isochrone matching. So based on the observed properties of the star and the known host cluster properties, can we get, we are able to get, I should say, the stellar evolutionary phase and initial mass of the variable. And just to highlight, this figure on the right shows the host cluster isochrone with the observed properties of the star just above it, the cross above, and the ellipses shown here are the extent of its measured variability in magnitude and color. So in this isochrone matching, we try to take into account the observed variability of the star, because we appreciate that it may not, or is likely not to be at its equilibrium state in its variability cycle, whatever the cause may be. And so the result, just boiling down to it, is we are able to identify 89 cluster variable stars. And these are the 2 key distributions. So we've got the initial stellar mass on the left and stellar evolutionary phase on the right. And I can almost certainly guarantee there's 2 things that have stood out to everybody: the very high number of low mass stars and the high proportion of post-AGB stars. And yes, they are directly linked, those 2. So the post-AGB stars, because of the age of those stars, are unlikely to be in that higher proportion. But you'll notice there's a gold, silver, bronze ranking to these histograms. And that basically reflects the fact that, yes, we've got 89 variables where the light curve varies and there is a source in a different image that has changed. But because of the highly crowded cluster environment, so in other words, light blending, and the quality of the source detection in the difference image, we attribute a different quality, confidence level, I should say, to each of these results. And that's what this reflects. So we can say, yes, 89 objects have changed. This also shows how confident we are that is that star changing. There's no blended light, or unlikely to be additional blended light, etc. And so this is the final color magnitude diagram that's produced. So you can see these stars cover a broad range of colors and magnitudes. And as I said, we are able to classify all these variables. So just to briefly highlight a couple of groups of them. So we've got the red supergiants up in the top right. All those stars have masses greater than 9 solar mass, so initial masses greater than 9 solar masses. The candidate super AGB, we emphasize candidates. There is only one potential super AGB known. This is definitely worth a follow-up, but again, crowded cluster environments, are we then seeing the same star, but it's a potential follow-up. And of course, Myra variables and Alpha Cygni stars as well. There are, of course, a number of caveats. I won't go through all of these, but the key ones really are, as I've said, cluster environments are highly crowded. So perhaps the greatest caveat is all the cluster stars in our sample will be affected by blending to some degree. So that's why part of the reason we brought in this confidence level criteria as well. And the sparse fat light curve, as I showed right at the start, means we're only able to provide a lower limit on the variability of these stars. But this is something where Roman, or again, even if it was not a targeted survey by Roman, even extending these light curves a little bit more would potentially massively increase the number of detections or the confidence in those detections. And so this is my very brief summary slide. So as I said, we've identified 89 M31 cluster variable stars from the Panchromatic Hubble Andromeda Treasury survey. But the key takeaway for this conference, I think, is that, yes, we've identified these 89 stars, but they're identified from a Hubble survey not designed in any way really, or purposefully designed for time domain. And so it was spatially limited. It doesn't cover the entirety of M31. And as I say, it wasn't a time domain survey. So what could we actually do with Roman? Either a targeted survey, that would be fantastic, but even the regions that by chance do different combinations of surveys and user input surveys are overlapping that allows us to get similar coverage. I think that's just a really exciting prospect, actually, even just based on this. And I can see time's up, so I'll leave it there and take any questions.
Thank you, Richard. Do you have any questions?
Hi, this is Robbie Wilson from NASA Goddard. This is really cool, and I was wondering if you thought about implications for whether you can do this with integrated star clusters for more distant galaxies to be able to detect like high luminosity, giant variability, something like that.
We haven't considered that actually, but it'd be great to chat to you over coffee. It's probably the best place to chat about it. But yeah.
Very interesting. Extragalactic variable star astronomy like this is just a lot of fun. One question is, if you were thinking about Roman, what kind of timescales, what kind of cadences would you be looking for? I would imagine these are pretty long period variables that you're looking at here.
Yeah. So as you saw at one of the earlier slides, so the light curves are roughly about 6 months apart. So we aren't really able to, or for most of the variables, we haven't been able to narrow down the classification based on the light curve information other than the amplitude. But it's one thing we have been considering. So for Roman, whether it's a much broader survey, sort of a catch-all variable survey, then you'd have to account for much shorter variables, day timescales or shorter, as well as longer timescales. Or I think perhaps the best solution would be a targeted survey, for example, looking at Myra variable, or trying to detect Myra variables only, or Cepheid variables, rather than a catch-all, just to perhaps increase the chances of getting the proposal in and also producing the detections. But as I said, I think with this study, what we've been surprised by is the fact this wasn't designed for this. Any overlap in Roman could produce something similar, if not hopefully better, if there are multiple repeat exposures of a certain patch of sky, for example.